Hello everyone, in this work, we present GarSim, a particle-based neural garment simulator. GarSim can simulate garments of arbitrary types, varying fabric, and topologies, on arbitrary body shapes and poses. It takes a canonical body mesh, a template garment mesh, fabric type, and the target body mesh as an inputs, and produces the displacements for the garment vertices to get the final simulated garment. Existing methods majorly work for specific garment type, or garment topology, and needs retraining for new type of garment. Some methods focus on a particular fabric, body shape, and pose. To circumvent these limitations, we propose GarSim. Our contributions in this work are a unified garment simulator that can simultaneously learns deformation of multiple type of garments, example, tops, skirts, etc., of varying topologies and fabrics conditioned on the underlying body shapes, pose, and motion with respect to the canonical pose. A particle-based approach that exploits the relational inductive bias in the garment data and helps generalize to unseen body shapes, poses, and garment types. GarSim can be trained and tested on the arbitrary resolution garment meshes. GarSim learns to simulate the garments using the concepts from particle-based modeling. We represent the state of the garment as particles, corresponds to the garment vertices, which encodes various garment and body-specific factors that affect its dynamics. In our case, the dynamic is the vertices displacements, direction and the magnitude, which is be computed based on the particles' interaction within their local neighborhoods. GarSim operates in a three-step process. During the first step, it embeds the particle-based state representation of the garment into the latent garment graph. It encodes the various garment and the body-specific factors into the nodes and edges of the garment graph. The encoded garment graph is then passed to the second step called processing step, where a learned message passing algorithm is used to update the state, node features, and their relationships, edge features, and output the final updated latent garment graph. Finally, the updated latent garment graph is passed to the third step called decoding step that predicts the direction and the magnitude of the displacement. We train GarSim with both the supervised and unsupervised losses. We evaluate GarSim and compare it with the DPSD on Cloth 3D dataset. The results in the table shows GarSim, despite being trained on low-resolution meshes, outperforms DPSD, trained on high resolutions, in all metrics. It shows that GarSim trained with a small amount of data accurately learns the physics of garment deformation. Qualitative comparison with PBNS, DPSD, Deep Draper, and the Taylor net. Notice the non-smooth surface, floating straps, and collisions in the PBNS and DPSD. We can observe the cloth quality predicted by PBNS is not good, irregular mesh surface, the straps in PBNS are floating in the air, and garments are colliding with the body, while GarSim produces significantly better pose-aware deformations and straps are resting on the body. We show generalization of the GarSim. In the figures we show textured qualitative results of seen, tops and skirts, and unseen, t-shirt and trousers, garment types on unseen body shapes and poses from YouTube videos. Fabrics based on their stiffness can be ordered as leather greater than denim greater than silk, and intuitively it is expected that the mean garment to body distance should also follow this order. The chart in figure empirically verifies this order. The prediction of the leather skirt, green, on top of the silk skirt, orange, visually verifies that GarSim produces the fabric-aware deformations. Finally, we show the video results. Notice the dynamics, the predicted garments follow the underlying body motion accurately, especially in the case of loose skirts. Thank you for watching. Please visit our project page for more details.